Hi everyone, this video is on the mixed exercise 9 question 40. So we have the curve C with the equation y is equal to ln of sine x, where x is between 0 and pi. So in part A, we want to find the stationary point of the curve C. So it's important to pay attention to these small details because the question is telling us that there is only one stationary point. And okay, if we want to find a stationary point, we need to differentiate the function and then set the derivative equation equal to 0 and then solve that. So the answer to that is going to be the x coordinate of the stationary point. So in this case, if you want to differentiate y, remember that if we have ln of any function and we want to differentiate that, we always differentiate the function inside the ln, and that goes in the numerator, and then whatever the function inside the ln is, that goes to the denominator. So in this case, the derivative of sine x is minus cos x. Sorry, it's just sine x. The derivative of sine x is cos x. Yeah, I just mixed up. Yeah, the derivative of sine x is cos x, and then the denominator is just going to be sine x. Yeah, and this is the derivative, which can be written as cot x. Yeah, so if you want to find a stationary point, we need to solve cot x is equal to 0. And just remember that the possible values of x are between 0 and pi. So this means that there is actually only one value in this domain that satisfies this condition, and its cut is just 0, and that value is simply pi over 2. So that's the only value that works here. And so that's the solution to the equation, and this is the x coordinate of the stationary point. So in order to find a y coordinate, we just need to substitute pi over 2 into the main equation, which is ln sine x. So we can say when x is pi over 2, then y is equal to ln of sine of pi over 2, and that's just equal to 0 because sine of pi over 2 is 1 and ln of 1 is 0. Okay, so the stationary point has the coordinates of pi over 2 and 0. So this is the stationary point. Okay. Now that we have the coordinates of the stationary point, let's now answer part B. So in part B, we need to show that the curve C is concave at all values of x in the given domain. Okay, what this means is that whenever we want to determine if the curve is concave or convex, we first need to find a second derivative. And once we have the second derivative, then we just need to show whether the second derivative is positive for the certain values of x or negative, and that determines if the function is concave or convex. And if the second derivative for a range of values of x is negative, then in that case we say the function is concave, and that's exactly what we are trying to show here. So we are aiming to find a second derivative and then show that that's negative for all the values of x between 0 and pi. So in that case we can conclude that the curve is concave. Okay, so let's find a second derivative now. So d squared y dx squared is equal to, this is part B, by the way. So we can use the quotient rule to differentiate cos x over sine x, because that's the first derivative. So the quotient rule says we can square the denominator. So that's going to be sine squared x. And then the denominator, the function in the denominator, times the derivative of the numerator function. So cos x differentiates to minus sine x. So sine x times minus sine x is minus sine squared x. Then minus, this time, the numerator function times the derivative of the denominator function. So cos x times the derivative of sine x, which is just, again, cos x. So it's going to be minus cos squared x. And we can simplify this. So let's take a factor of -1, and it's going to be sine x squared plus cos squared x. And this is the numerator, and the denominator is just sine squared x. So the numerator is going to be 1 because it's an identity. Therefore, we are going to have -1 over sine squared x. So let's just get right here. So it's going to be -1 over sine squared x. And just remember that 1 over sine x is cosec x. So in this case, this can be rewritten as minus cosec squared x. All right, so this is the second derivative. Now, what we need to show is that actually just sticking to the general form, I mean the original form, which is -1 over sine squared x, that's probably the easier format to use in this case. Because remember, ultimately, we want to show that the second derivative is negative so that we can conclude it's a concave curve. So yeah, using the -1 over sine squared x format is probably the easier one. Okay, so we need to remember that, or just notice that 1 over sine squared x is obviously always positive, right? Because no matter what you get in the denominator, it's going to be a squared, and then it's always going to be positive. So as a result of that, 1 over sine squared x is always positive. And therefore, this means that if you have -1 over sine squared x, then this is always going to be negative, because no matter what you get as the entire thing, which is always going to be positive, you also have a negative, which makes that negative. So we have kind of shown that, you know, -1 over sine squared is always negative for all values of x which are between 0 and pi. So therefore, we can say that the second derivative is always negative for all values of x between 0 and pi. And yeah, so, and since that's the case, hence C is concave. And that was what we were trying to show from the beginning. Okay, so that's it for this video, and thank you for watching.